Welcome to this week's Short Clip Friday podcast. Each Friday, I'll be posting 10 to 15 minute segments from previous podcasts. And the point here is just to bring you some of the highest yield topics from each podcast in order to kind of reinforce those topics. This clip is from the Acids and Bases podcast and covers pH calculations. Enjoy. Let's get into calculations involving acids and bases. The most common problem you're going to see involving acids and bases on the MCAT is calculating pH. And so this should be a breath of relief for you. Calculating pH is super easy. However, it's a place where you can make you can make a mistake easily. And so I'm going to go over how not to make these mistakes. So when you're calculating the pH for a strong acid, it's very straightforward. You just need to use the concentration of reactants to calculate the hydroxide ion concentration after this reactant has fully dissociated. And then you use the equation, pH is equal to negative log of your H plus, and boom, you got pH. So when you're doing this, you need to take into account stoichiometry. Stoichiometry is where a lot of people have problems, including myself, so it's a place you really need to pay attention to when you're doing acid and base calculations. So say you have a 1 molar solution of sulfuric acid. So remember, sulfuric acid is H2SO4, and it really might ask you sulfuric, so make sure you know names and also how many hydrogen are with each strong acid. So 1 molar sulfuric acid, what is the pH of that solution? So you look at sulfuric acid, H2SO4. If it were to fully dissociate, you'd have 2 protons per 1 mole of H2SO4. So for each H2SO4, you have 2 protons when it dissolves. So you have a 1 molar solution. You got to multiply that by 2 because you have 2 hydrogen per mole of sulfuric acid, and that's 2 moles of hydrogen ions. So then you do negative log of 2, which is negative 0.3. That's not right. Boom, that is right, negative 0.3. So something also to remember, and this is a good example, is that pH can be negative. It's not physically impossible for it to be negative. It's not like in physics where you're calculating a distance and you get a negative distance and you're like, shit, that can't be. You can have a negative pH, and as Tupac says, sometimes that's just the way it is. Let me briefly summarize what I just discussed. So for a strong acid, find how many hydrogen ions dissociate, multiply that by the concentration of your reactant, plug that into negative log of H plus, and you have the pH. And for POH, it would be the exact opposite process. Well, it would be the exact same process, but you do that with hydroxide ion or OH minus concentration. And don't forget that the lowercase p of anything is the log base 10 of that thing. So, you might see some notation on the MCAT where it says little p of, anything. For example, take density, p, little lowercase p, rho, which means density. That would just mean the negative log of density. And so after I talk about weak acids, I'm going to go through how to quickly do logarithms in your head, another great skill to have on the MCAT. So calculating the pH for a weak acid is a bit more complicated. You need a dissociation constant, which is a Ka or Kb, depending on Ka is acid dissociation constant, Kb is base dissociation constant. And you're definitely less likely to see this on the MCAT, but I would still know it. And so if you think back to freshman chemistry or even AP chemistry in high school, think back to ice table. And these are a quick way, you just draw it up on your little board you have for the MCAT when you're taking it. Drop a little ice table and solve it. And so, again, the I stands for initial, the C stands for change,
and the E stands for equilibrium. And so if you remember, a dissociation constant is simply an equilibrium statement. So it's just the concentration of the products over the concentration of the reactants.
And each of these concentrations is raised to the power of their stoichiometric coefficients.
And it just simply says, if you were to leave this reaction sitting here for all of time at this infinite time point, the concentrations would be boom. And so, so concentration products over the reactants
raised to the power of their stoichiometric coefficient,
and that's equal to Ka or Kb. So that just tells you what those concentrations are. And so first thing you do, fill out your ice table. You have your initial. Usually you know the concentration of the reactant, and you do know the concentration of your products because they're zero. And that initially they're zero. And then you fill in the change, which is usually in X because it's unknown. And then you fill out the equilibrium part, which is where you say, okay, initial minus your change is equal to your equilibrium concentration. And then you take these equilibrium concentrations and you plug it in to your dissociation constant you plug it into your equilibrium expression, which is concentration of products over concentration of reactants. And then you go ahead, you solve for X, and then that's your change. You plug it back in and you find your end concentrations. Pretty easy, kind of. And from that, you can figure out, okay, this is how much protons disassociated, or you can find the proton concentration or the hydroxide concentration. And then again, you use negative log of your proton concentration, which is pH, or POH is your negative log of your OH concentration. And that is how you solve that.
All right, so let me just quickly summarize what I just went over. So when you're given a weak acid problem, you're most likely going to be given the concentration of this weak acid or weak base, and then also the Ka or Kb. And then what you want to do from there, draw an ice table, fill in what you know. What you don't know, label with X. Once you have that all filled out, you can plug in your knowns and unknowns into your equilibrium expression. This is all going to be in terms of some variable X. Then you're going to solve for that X. Once you have that X solved, you can then solve for the hydrogen ion concentration. And then the easy part, the pH is equal to the negative log of the H plus concentration, or the hydrogen ion concentration. Same goes for POH, negative log of the OH minus concentration.
And so it's good to know also how to convert between POH, pH, and your concentration of H pluses, concentration of OH minus. So this is pretty easy to remember. pH plus POH must equal 14. So sometimes it's going to ask you to calculate the POH of an acid. And so this is kind of a trick question, right? Because you're thinking, okay, pH of an acid, or you're thinking POH of an acid, but you're kind of in your head, you're thinking pH, you're thinking acidity, and you miss that. And so don't miss that. You know, if your POH is low, that means that you have something that's a base, and if your POH is high, then you have something that's an acid. So it's the opposite of a pH. And then to convert between H plus and OH minus, you use Kw, which is the dissociation constant of water. And that is 1 times 10 to the minus 14. And so you have that your Kw is equal to your hydrogen ion concentration times your OH minus concentration. So keep in mind that this always holds. Your hydrogen ion concentration times your hydroxide ion concentration is always equal to 1 times 10 to the minus 14th. So you can convert between those as you wish. So I'm going to briefly touch on the quick and dirty logarithm calculation method that I used on the test, just, save time. So first, what is a logarithm? So a logarithm is the inverse function to an exponential. Basically, this means that the logarithm of some given number is the exponent to which another number, say 10 in this case, must be raised to produce that number. In other words, let's say you have log base 10 of, in parentheses, 5 is equal to x. What that's really saying is 10 to the x is equal to 5. What number is x in order that 10 raised to that power is 5? So essentially, what you can do is when you have a hydrogen ion concentration, put it in scientific notation right away, always. And once you have it in scientific notation, you're going to have, negative log to the 1 times 10 to the minus 4, for example. All you do is you take that exponent, multiply it by a negative 1. So log base 10 of 1 times 10 to the minus 4 is equal to 4. So if your hydrogen ion concentration is 1 times 10 to the minus 4, then your pH is 4. So just pick out the exponent each time. Negative log of 1 times 10 to the negative 5th, that's a pH equal to 5. Negative 6, pH equal to 6, and so on. Of course, this gets more complicated when the multiplier out front is not 1, and you can just use an estimation in this case. So let's say you have negative log of 3 times 10 to the minus 4. Well, the exponent is negative 4, and so that's the first thing that should come to mind, negative 4. However, the leading coefficient is 3, or the leading number is 3. So you know that this number has to be between 3 and 4. Because this is a negative log, you have to go down. So I think the tendency here is to say, okay, 3 times 10 to the negative 4 is a bigger number than 1 times 10 to the negative 4. However, that pH is actually lower. So the tendency here is to say, shouldn't it be between 4 and 5 because you have 3 times 10 to the minus 4? It should actually be smaller because of that negative leading part to the log. So the actual answer here is that the negative log of 3 times 10 to the minus 4 is 3.5. However, as you know, you don't have a calculator for the MCAT. So usually, and I say usually because I don't know exactly for sure, but every case I've seen, I'm able to just estimate this number and kind of pick it out. It's never, there's never question of, okay, there's two numbers it could be two numbers, which one is it? I know the answer is between 3 and 4, but there's 3.5 and 3.2, which one is it? Everything I've seen, you can just estimate it and say, okay, this number is between 3 and 4. I'll pick 3.5 because that's the only one that's between 3 and 4. So again, negative log, pick the exponent out if the multiplier is 1. If the multiplier is above 1, you go down. So you say, okay, the exponent is negative 6, and the multiplier is 5. Well, I know it must be between 5 and 6.